In quantum mechanics, we have something called operators that we have to regularly deal with. You see, in quantum mechanics, we do not deal with the physical quantities themselves, but instead we deal with their corresponding operators, because it is the operator which is capable of revealing some information about that physical quantity in a quantum mechanical system. So for example, if we have some sort of an operator, let's suppose A hat, and I want to find the average of the physical quantity in that system, then what we do is we take the expectation value of that particular operator, which simply means that we take the wave function complex conjugate, we take the operator acting on the wave function, and we integrate from minus infinity to plus infinity for a particle restricted to 1D motion. Now this gives us the average of that physical quantity corresponding to which A is an operator. Now, where does Hermitian operators come or arise in this particular context? You see, the physical quantities themselves must be real, whether we talk about energy, momentum, position, angular momentum, their average has to be a real number. So in that sense, the operator and its expectation value the expectation value of the operator should also be a real number. That means if I take the complex conjugate of this expectation value, it should come out to be a real number. So if I do a complex conjugate of this particular expression, then quite simply put, it takes this form. Okay, if I write it in detail, this is how it looks. All right, now both of them are supposed to be equal, especially when we are dealing with physical quantities, because physical quantities and their averages are real numbers. This is where Hermitian operators come into the picture, because if I look at the detailed nature of this expectation value, which is essentially an inner product of the operator sandwiched between psi and psi for the top expression, and if we look at the bottom expression, this is essentially the operator acting on psi star, which is basically written as Hermitian adjoint of the operator acting on psi star and the inner product with respect to psi, then both these expressions are essentially equal for Hermitian operators. Therefore, Hermitian operators in quantum mechanics are a very special case of operators that satisfy a very simple expression, which is that the operator itself is equal to its Hermitian adjoint. Now the question I want to answer in this particular video is, if we are dealing with some kind of an operator that looks like this, a derivative with respect to x, is this a Hermitian operator? And what I want to answer eventually is, what if I take a nth order derivative? What if I take something like, let's suppose, a to the power n, so dn to the power dx to the power n, is this a Hermitian operator? And to prove whether or not the derivative with respect to x is a Hermitian operator, all we have to do is plug this expression into our definition of a Hermitian operator. So for example, in this kind of a scenario, the expectation value of the derivative with respect to x is simply psi star d psi upon dx and integrated with respect to x. Okay, this is the first expression. Now for a Hermitian operator, if d upon dx is a Hermitian operator, then this should be equal to the complex conjugate of the expectation value of a. So in this case, this is nothing but the second operator, which is psi d psi star upon dx integrated with respect to x. So let us see if they are equal or not by expanding this second expression. So if I expand this second expression, because psi here is a function, so is d psi star upon dx, I can use integration by parts. And if I use integration by parts, this should become psi integration of d psi star upon dx, and this is integrated with respect to x, minus d psi upon dx, and again integration of d psi star upon dx integrated with respect to x, and this whole integration is also integrated with respect to x. Okay, hope this doesn't get too confusing. Integrated between minus infinity to plus infinity. Now if I simplify this a little bit further, it becomes kind of clear what I am talking about. That what is this? If you look at the first expression, this is essentially integration of d psi star, which is nothing but psi star between the limits of minus infinity to plus infinity. And if we look at the second expression, this simply becomes psi star d psi upon dx, because this is the same as this particular expression, integrated with respect to x from minus infinity to plus infinity. Now in quantum mechanics, when we are dealing with various wave functions, especially for particles, then we have to impose certain kinds of restrictions on the wave function to make sure that it is normalizable, that it has a smooth and continuous probability density distribution along the x-axis. So one criteria is that whether we deal with the wave function or whether we deal with its complex conjugate, at the end of the day, both of them should go to 0 at infinity. Okay, whether we look at the wave function or its complex conjugate, it should go to 0 at plus minus infinity. So it means that this first expression goes to 0. Therefore, this is essentially nothing but psi star d psi upon dx integrated with respect to x from minus infinity to plus infinity. Now make a very simple comparison between the expectation value of this operator and its complex conjugate. You can clearly see that they are not equal when the operator is d upon dx. So if they're not equal, it means that number one, this is not a Hermitian operator. D upon dx is not a Hermitian operator. That is the first conclusion that I can make. All right. So this is very important, that the derivative with respect to x is not Hermitian. However, because the second expression involves the Hermitian adjoint, I can now also make a conclusion that here the Hermitian adjoint of d upon dx is equal to nothing but a negative sign is introduced between the expectation value of d upon dx, which is essentially minus d upon dx. Okay, now this will serve as a helpful expression that will help us in figuring out what happens to the higher order derivatives. So now the calculation is very simple. So the d upon dx derivative is not Hermitian, but if I take a look at, let's suppose iota d upon dx, what about this operator? If I just include the iota term, the complex, this imaginary term, then what happens here? Now I can again plug this in the same fashion in my detailed derivation to come up with a conclusion, but I don't have to do that. Things becomes much simpler at this point, that if I simply take the Hermitian adjoint, because iota is a scalar, therefore this becomes complex conjugate of this, and the Hermitian adjoint of this is simply minus iota. Complex conjugate of iota is minus iota, and the Hermitian adjoint of d upon dx, which we have proved, is minus d upon dx. This is equal to iota d upon dx. So you clearly see that iota d upon dx Hermitian adjoint is equal to iota d upon dx, which means that, important point, that iota d upon dx is Hermitian. Why? Well, if you are familiar with the various operators in quantum mechanics, one very important quantum mechanical operator is the momentum operator. What is the momentum operator? Minus iota h cross d upon dx. You see, h cross is, by the way, a constant, so minus is also a constant. So iota d upon dx has to be Hermitian, otherwise the momentum operator wouldn't be Hermitian. You see, all physical quantities and their operators are Hermitian by our definition initially. So this is a Hermitian operator. Okay, but now let's move on to a little bit of a higher order operator. So what if I take something like the second order? So d2x upon dx2. What is the Hermitian adjoint of this? The Hermitian adjoint of this is quite simply put d upon dx Hermitian adjoint and d upon dx Hermitian adjoint. What is this? We have already proved that the Hermitian adjoint of d upon dx is minus d upon dx. So this comes out to be d2 upon dx2. So you can clearly see that even the second order derivative here is a Hermitian operator. So d2 upon dx2 is Hermitian. All right. Can you name some kind of a physical quantity whose operator contains the second order derivative? The kinetic energy operator. If you're familiar with the kinetic energy operator, it is nothing but minus h cross square upon 2m d2 upon dx2. So clearly these two expressions are Hermitian. So iota d upon dx is a Hermitian operator. d2 upon dx2 is also a Hermitian operator. What if some random nth order derivative with respect to x? We can sort of make a deduction based on looking at how things progress. So for example, what if I take d cube upon dx cube? What is this? Again, I can do the same thing. Hermitian adjoint of d upon dx, Hermitian adjoint of d upon dx, and Hermitian adjoint of d upon dx. This essentially becomes minus d upon dx minus d upon dx minus d upon dx. So essentially this is equal to minus d cube upon dx cube. This is not equal. So that means the third order, so d cube upon dx cube is not Hermitian. But if I simply add an iota to this expression, so that means if I take iota d cube upon dx cube, now it will become Hermitian. So iota complex conjugate d cube upon dx cube Hermitian adjoint is equal to minus iota minus d cube upon dx cube. This is equal to iota d cube upon dx cube. So you see that iota d cube upon dx cube is Hermitian. So from here we can make a simple kind of a deduction. So if you look at the first order derivative, which is d upon dx, this is not Hermitian, but it becomes Hermitian when I include the iota term in the expression, iota d upon dx. The second order derivative is Hermitian, so I don't need to do anything there. The third order derivative is not Hermitian, but it becomes Hermitian if I include iota d cube upon dx cube. So I can sort of see the pattern in which these things are evolving, and I can make a very simple conclusion that if I have some kind of a nth order derivative, so dn upon dx to the power n, here if n is an odd number, or let's say if n is even, then it is Hermitian. Okay, if n is even, then it is Hermitian. But if n is odd, then it is not Hermitian, but we can make it Hermitian by multiplying with a complex conjugate. Or I should say, sorry, imaginary number, iota, Hermitian. So this gives you a general idea about some random nth order derivative. So if I say, what about d 5 upon dx to the power 5? Is it Hermitian? What about d 64 upon dx to the power 64? Is it Hermitian? Write your answers in the comment section. Let's see if you have understood this topic or not. So the first order derivative is not Hermitian. It becomes Hermitian when I multiply with the iota term, and the rest is in front of you. That is all for today. If you guys are interested in competitive examinations in India like Physics IITJAM, CSIR-NET, GATE, then we have regular live batches as well as recorded courses in our Elevate Classes platform. We have an upcoming batch for CSIR-NET June 2025 and GATE 2026 physics starting 22nd December. You can visit our website or you can download our app and you can join our course. That is all for today. I am Divya Jyotidas. Thank you so much. Take care. Bye-bye.